Okay, so today what we're going to do is we're going to study the kinetic theory of gases. What this means is, so let me show you a simulation. So here's this is a simulation you'll use for one of the labs. So let's fill this chamber with some gas. Okay. So a gas is a bunch of molecules, and as you know, we are studying thermodynamic systems. Thermodynamic systems are systems which have a large number of particles, okay? And when we say large, we mean sort of Avogadro's number, something close to Avogadro's number. Anyway, a large number of particles, okay? And see what this graph is showing you is this speed of the particles versus the number of particles, okay? So you see all the particles are not moving with the same speed. You have a distribution, and this distribution is actually called the Maxwell-Boltzmann's distribution, which we'll study. Okay, so what this chapter is about is we'll relate the microscopic properties, meaning like the kinetic energy of the particle, to macroscopic variables. So for this system, what we can measure is pressure, temperature, and volume, and a few other parameters. Okay, and these guys can be measured using large macroscopic instruments. Okay, so what this chapter is going to do is we're going to relate the kinetic energy of a tiny molecule to the temperature which is measured using a macroscopic instrument, pressure which is using a macroscopic instrument. Okay, so that's what this chapter is about, relating microscopic quantities to macroscopic quantities. Okay. All right, so the kinetic theory of gases. So we'll start off by studying the ideal gas law. You guys all know what the Avogadro's number is. We'll see how pressure, temperature, and RMS speeds are related. Mean free path, you saw that in that simulation as the molecules are going about, they're colliding billions of times a second. Okay, so of course this simulation can't show you that, but they're traveling billions of times a second, and so here's the path of a single atom, and you can see that this is taking a random path, and the mean free path is the mean distance it travels before colliding with another atom or the walls. Okay. So that's the mean free path. We'll talk about the distribution of molecular speeds, and so on. And then we'll talk about molar specific heat. Okay. And this is a very important point as well, the equipartition of energy, and you'll understand it when we get to it. Okay, so let's get started. Now, you guys all know the ideal gas law. So let me write down the ideal gas law. So you all have seen the ideal gas law. PV equal to nRT, or it's also written as PV equal to nKT, where K is the Boltzmann's constant. Now, you've seen this in chemistry classes and all that kind of stuff. But this law was discovered in stages, okay? And so here it is, Mr. Boyle. So this law was discovered between 1660 and 1800, so over a span of 140 years, and in stages, like I said. So what Mr. Boyle discovered was that pressure and volume of a gas are inversely related at constant temperature. Okay, so what Mr. Boyle discovered was if you keep the temperature constant, this is constant, and the product of pressure and volume is constant. Okay, so that's what Mr. Boyle discovered. And so what he found was at constant pressure, so pressure and volume are inversely related. Okay. Then Then almost 100 years later, Mr. Charles found that at constant pressure, the volume of a gas is proportional to its temperature. So what Mr. Charles found was at constant pressure, if P is constant, then volume is proportional to temperature. That means you double the temperature, the volume doubles. Okay. And that took another 100 years. Okay. And then finally, Mr. Gay-Lussac found that when the volume of a gas is held constant, its pressure is proportional to temperature. Okay. So about 25 years later, Mr. Gay-Lussac found you keep the volume constant and pressure is proportional to temperature. So you double the temperature. Oops. So when volume is constant, pressure is proportional to temperature. So you double the temperature, the pressure doubles. All right, so with all these laws, we could put together, with the three formulas, we could put together the ideal gas law finally. Okay, and so that's how come the ideal gas law came about. Now, again, one last thing was in 1811, Avogadro found that the ratio of the volume to number of particles is constant if the pressure and temperature are constant. So the last piece of the puzzle was Mr. Avogadro found that V over N is K T over P. Okay. So this gives you the number density of molecules. So if temperature and pressure kept constant, then V over N is constant. Okay. And so that's how come the ideal gas law was discovered over, like I said, over a span of 150 years. Now, what this graph shows you is, so this is a two-dimensional surface plotted on pressure, volume, and temperature with those three thermodynamic parameters. So you take an ideal gas and you take a bunch of ideal gas, let's say 3, 4, how many ever moles. And as long as you keep the number of molecules fixed, so if you keep the number of molecules fixed, the gas will remain on this surface, okay? So no matter what you do to the gas, it just moves around on this surface. And these various laws are just slices of this surface along the various axes. So if you keep the temperature constant, you're taking a slice perpendicular to the temperature axis, and you get Boyle's law. So if you take a slice perpendicular to the temperature axis, you get that. If you take a slice perpendicular to the pressure axis, you get Charles's law. And if you take slice perpendicular to the volume axis, you get Gay-Lussac's law. Okay, so these are just various slices of this surface. Okay, and like I said, they were discovered over a span of 150 years. Okay, but now you guys are, I mean, this is one of the first things you learn in college. Okay, so you're familiar with the ideal gas law. All right, so again, this shows you the various slices. There's the surface. There are the three axes, the three thermodynamic variables: pressure, volume, and temperature along that axis. Okay, and these green lines, which are hyperbolas, are slices of the surface taken perpendicular to the temperature axis, and so on. Okay. All right, so there is the ideal gas law: pressure, volume, pressure times volume is equal to N is the number of moles of gas you have. R is the gas constant. There's the value of the gas constant, 8.314 joules per mole per Kelvin. And in this formula, the temperature is measured in Kelvin scale. Okay. So again, So from this formula, you can see that as you decrease the temperature to absolute zero, the pressure will go to zero and the volume of the gas will also go to zero. Okay. So in this ideal gas law, we are assuming the volume of each of those molecules is very, very tiny. So they're essentially point particles. Later we'll make corrections to these, but anyway, what this ideal gas law assumes is these gas molecules have a negligible volume. They have negligible intermolecular forces. So when they feel each other only when they collide. Okay. So that's what all that is incorporated in this ideal gas law. Okay. And by the way, 1 mole of any gas, any ideal gas at atmospheric pressure at 0 degrees Celsius occupies 22.4 liters. A gallon is 3.8 liters, right, or under 4 liters, so almost 6 gallons. Yeah. So here's the there's the ideal gas law in terms of the number of moles, and here's the ideal gas law in terms of the actual number of molecules. And R is the gas constant, Kb is the Boltzmann's constant. Okay. So it turns out that R and Kb are related, and they are related like so. R is Avogadro number times the Boltzmann's constant. Okay. And you all know Avogadro's number is 6.02 into 10 to the 23 molecules per mole. And the Boltzmann's constant is 1.38 into 10 minus 23 joules per Kelvin. So anyway, you often see the ideal gas law in these two forms. This is the number of moles and this is the number of molecules. Okay? And the two are related. All right, so there's the Boltzmann's constant. Okay. And again, the ideal gas law is given in terms of these 3 thermodynamic variables. Okay, so here's again the surprising, amazing thing about it. So here you have a trillion molecules. Well, not here, but you know, the behavior of a trillion molecules in equilibrium is described by just a handful of thermodynamic parameters. Okay. And that's the neat thing about it. Okay. So 1 mole of a substance is 1 mole of any substance is that many particles of that substance. Okay, and that's the Avogadro's number. And the Avogadro's number is an experimentally found number. Okay. So here's, you guys know from your chemistry classes, for instance, that how do you figure out, do you have a mole of some stuff? So for instance, if you have methane, the molecular mass of methane is 12 for carbon, plus 4 times 1 for hydrogen. It's 16 atomic units. And if you take 16 grams of methane, you have 1 mole of methane. And so that's how that works. And 1 mole, when you have 1 mole, you have 6.2 times 10 to the 23 molecules, methane molecules. Okay. So that's how the mole works. Okay. So 1 mole of any substance is the amount of substance that contains Avogadro's number of particles. Okay. Just to give you a sense for how large this number is, Avogadro's number. So here's a nice little thing from your textbook. So if you take ping pong balls, table tennis balls, and you took 1 mole of table tennis balls and threw it on Earth, they would evenly spread out on Earth, and they would make a layer that thick. And there is Mount Everest, which is 9 kilometers tall. Okay. So that's, Avogadro's number is really a big number. Okay. And this thickness is 40 kilometers. Okay. Now, the ideal gas law that you see assumes that these molecules have very little volume, so they're essentially treating them as point particles, and also there's no intermolecular forces between them. Now, that is true if the gas is dilute, and in fact, well, in most situations that we encounter, well, in most situations that we handle, we will assume that. But if you take a very dense gas, then that's not true. And here's a correction to that. Okay, so this is a correction to the ideal gas law. Again, so the ideal gas law is PV equal to nRT. Okay, so here's how we correct for the fact that the gases have finite volumes. So in this formula, volume is the volume that the space that the gas molecules have to run around in. Okay, so what we'll do is, so for the corrected gas law, so we'll subtract this by some constant. So this term is this is the number of moles of gas you have, and this is the volume that 1 mole of that gas occupies. So now V minus that gives you the space that the gas has to run around in. And similarly, because the molecules attract each other, the pressure is actually less than this pressure. Okay, and that's some constant times the density of the gas molecules. Okay. So anyway, so that's how we'll correct. That's how. Okay, well, that's that term is positive. This term has to be positive because the pressure is less than the actual pressure, and the actual pressure plus this correction term gives you that term in the ideal gas law. All right, so for a non-ideal gas, this is the correction. Now it turns out that in the low density limit, the term containing A and B are negligible, and one gets the ideal gas law back. So when these two, this term and this term are very small, you get P times V equal to nRT. Okay. Anyway, I just wanted to show you this equation, which you don't come across often. Okay, so this is the gas equation for non-ideal behavior. All right, we'll talk about Dalton's law. Okay, so let's go to this simulation. And again, like I said, you'll be using this simulation for the lab. So let's add some molecules of slightly different variety. All right, now if you have a mixture of gases in a gas, if you have a mixture of molecules in a gas, okay, so for instance, our atmosphere is like that. Our atmosphere is 78% nitrogen, 21% oxygen, and 1% of some other stuff. But so it's mostly nitrogen and oxygen. Right, so if you have a mixture of gases, and let's say the pressure, see the pressure of this gas is 60 atmospheres. Okay. What Mr. Dalton found was the total pressure is the sum of partial pressures. Okay. What this equation is telling you is, so for this gas, the pressure is 60 atmospheres, And so if the blue molecules exert a pressure of 40 atmospheres, the red molecules are exerting a pressure of 20 atmospheres. That's what Dalton's law says. That's what Dalton's law says. And also, the partial pressure of each gas is proportional to the fraction of the gas. Okay. The molecules and the blue molecules exert is 1/3 of this, which is 20 atmospheres. That's what Dalton's law is. Okay. So the total is the sum of pressures, and the partial pressure of each gas is just the fraction of the total pressure, where the fraction being just what's the fractional content of the molecules. Okay, so that's what that means. Okay, your book gives you hello, can everybody still see me? You guys can hear me?
Yep.
Yep.
Okay. All right, something came up on the screen, and so I was wondering. All right, this is a table in your book. That gives you the saturated vapor pressure of water vapor. This is important in many areas. So what this means is that these temperatures, okay, when it's 100% humidity, the pressure due to water vapor is that much. So at 10 degrees Celsius, it's 1,000 pascals. And remember that atmospheric pressure is 100,000 pascals. So this is 1%. The partial pressure of water vapor is 1% of the atmospheric pressure. So at 18 degrees Celsius, it's 2,000 pascals, so it's 2%. So let me make sure. So what we saw was atmospheric pressure. 1 atmosphere is 10 to the power 5 pascals, which is 100 times 1,000 pascals. Okay. And at 18 degrees Celsius, the partial pressure of H2O was, water vapor was 2,000 pascals. Okay, so this is at 100% humidity. Okay, so, and that's partial pressure divided by atmospheric pressure is 2%. Okay. And of course, if relative humidity is 50%, then the pressure of H2O would be 1,000 pascal. Okay. So that's at 18 degrees Celsius. So anyway, this is a useful table, very useful table in meteorology. Okay. All right. What I'm going to do is I'm going to pause the recording now and let you guys ask questions if you have any.